Start again. So let's continue. So far what we learned about some fundamentals, how microbial electrochemical technologies works. We learned about EET, how actually you can have extracellular electron transport, right? And then we learned about different application, okay? So how we can actually manipulate different types of electron acceptor, and we can get different types of validated product or other application like biosensor. So now we are going to talk about one of the important aspect, okay? So which is basically we are going to learn about significance of different process parameters in for microbial electrochemical systems, and we are also going to actually talk about kinetics, okay? So we learned about kinetics for activated sludge process, and we are going to see how kinetics can also be applied for this kind of process. So substrate affinity, so those electroactive bacteria, okay, they can directly oxidize some organic contaminants like acetate, okay, but if you have fermentable substrate, okay, so let's say you have some complex substrate like glucose or protein or like some other compound, okay, they need some sort of partnership with some other microorganisms like some fermentative bacteria. So what happen if you have some complex substrate like glucose, it's not going to be directly oxidized by EAB, okay. So you need some fermentative bacteria, okay, they are going to ferment, produce some organic acid, and then that organic acid can be utilized by EAB. So we call this mechanism syntrophic interaction with non-EAB. So some bacteria, they are not electroactive bacteria, they degrade and their metabolite can be used by EAB. So but most of the studies in this area, okay, have been done with acetate as a substrate, okay. And why is that? Because we know that acetate can be directly utilized by microbes. So for some fundamental study, okay, acetate has been widely used as a model compound, okay. But for real life, you have to make sure that you have a balanced microbiome in your biofilm. You have both non-EAB like fermentative bacteria, and you have electroactive bacteria. So especially when you want to design something for real wastewater or complex wastewater, okay. Another major concern in this kind of process is proton accumulation in the biofilm, because if you remember your anodic reaction, if you have acetate, okay, that's going to be oxidized to carbon dioxide. The process also going to produce proton. You can see like 1 mole of acetate going to give you 7 mole of proton and 8 mole of electron. So that means you expect that, okay, when electron is moving from anode to cathode to maintain charge neutrality, your proton is also going to move from anode to cathode, right? But in reality that thing may not happen, okay. So that thing may not happen because that proton also concentration gradient is also important. Some other cations, okay, for some other cations concentration might be high, and instead of proton those other cation may actually move from anode to cathode to maintain charge neutrality. So not necessarily it has to be proton. Yes, we expect that ideal case is going to be proton, but in reality that may not be the case. So what would happen if proton is concentration kind of proton accumulate in the biofilm? It's going to increase or decrease your pH? Decrease, right? If you have higher proton concentration, then your pH going to decrease. But those microbes, they prefer neutral pH, right? But now let's say some microbes, they are going to be in inner layer of biofilm, some microbes can be in outer layer. For outer layer, maybe proton can easily migrate from the biofilm, okay, or maybe diffuse out of the biofilm and go to the cathode. But some microbes that actually they are doing this reaction and producing proton, maybe inner biofilm, that proton may accumulate, okay. Then those proton pH gonna drop and those microbes may be inhibited. So you might have a different zone, okay? You might have a different zone. So inner layer could be like inhibited or inactive zone, like dead microbes, and outer layer could be like more active bacteria. So that thing could happen as well. So that's why, like, you know, more thick biofilm, sometimes what we think, like, you know, if we have more active biomass, we have better process, right? But that may not be the case. You might have an inactive zone and active zone. Although actually when we do lab scale studies, we add buffer with our, you know, say electron donor. So we don't see pH drop. But if you don't have enough buffer in your wastewater, then that can be a problem, okay? So like during my PhD, actually I did some experiment. So, you know, like decreasing buffer content, and what I did, we had some sort of like microsensor. So we could see a different depth of biofilm, what is the pH, okay? So and I could see actually pH dropped near the actually electrode surface. And then we also did some, you know, like confocal microscopy with, you know, staining the biofilm with, you know, those live and dead cell that you could see. And I could easily see, like, you know, there are a lot of red cells. So that means dead cells inside of the biofilm, and outer layer is more like green cells, okay? So pH accumulation, proton accumulation or pH drop could be a major challenge for this kind of process. The same thing could happen for substrate, okay? So if you have a very thick biofilm, okay, outer, you know, like outer layer of biofilm, those microbes, they can easily get substrate. But maybe inner layer, there might be some substrate limitation. And you can have same, you know, problem. Like you can have some substrate limited zone, and you have inactive zone and active zone. So that's why actually the biofilm thickness or maintaining certain biofilm thickness that can actually avoid proton accumulation or substrate limitation, it's very important, okay? So thick biofilm doesn't mean that, okay, you know, you have more active biomass and you can have better performance. So sometimes actually, you know, like some researcher, they applied model like, you know, finite element method to actually, you know, kind of model this kind of substrate gradient inside the biofilm, okay? So those are actually kind of like, you know, combining Monod equation and Fick's law for diffusion, okay? So you can combine different biological model and diffusion model combined together and see whether you are going to have some proton accumulation inside the biofilm or substrate limitation, okay? Another way is you can use microsensor, but microsensor typically they are quite expensive, okay? So now we are going to have a very important topic. So on day 2 we learned about kinetics, okay? So we learned about kinetics, and what we did, we kind of used Monod equation. So what Monod equation is telling us? Can anyone volunteer? What is Monod equation telling us?
Kinetics of microbes.
Kinetics of microbes, yes. So this is actually Monod equation. If you remember mu max, anyone remember the equation? Ks plus S, right? So this equation is saying, okay, you know, like when substrate concentration is limiting, okay, so with increase in substrate concentration, growth gonna increase. So graph gonna look like this, mu, and at a certain substrate concentration, growth gonna reach maximum, right? That's Monod equation. So now researcher, they try to see whether, okay, we can apply that Monod equation, okay, and we can actually estimate. So one of the thing, output from the system is current density, right? So we kind of like, you know, microbes, they oxidize organic compound and then they actually produce current, right? Current density. So they are trying to see if substrate is only the rate limiting part, if we can actually describe this system using Monod equation or not, okay? And actually it was, well, I'm sharing it here, that means actually we can do that, right? So, so that's why I was telling, if you learn the kinetics or how to establish, you know, kind of model equation for one biological system, you can apply, then you can actually learn other biological system very easily. And that's actually the beauty of environmental biotechnology. Okay. So let's see how we can actually apply Monod equation for EAB biofilms, electroactive bacterial biofilm. So current profile to substrate concentration follow typical Monod pattern, okay, which is typical Monod pattern when substrate concentration is the rate limiting factor for current generation. So here we are seeing we are going to have substrate is the rate limiting, okay, but here growth, actually growth part, we are saying instead of growth we can consider the current density is the output, okay. So we use J for current density. Okay. So now, so the substrate utilization kinetics for microbial electrochemical system has been successfully modeled with Monod equation. And Monod equation, what we learned, substrate utilization rate equal to substrate, okay, minus Ts by dt equal to what? Substrate concentration, right? Okay, now we can put a proportionality constant, okay, mu s, right? So this is kind of like Monod equation, substrate utilization kinetics, right? So now you can see here, sorry, it depends on the not S, actually it's a biomass concentration, yeah, sorry. So mu max. So do you agree with that? It's good? Did you have a chance to go through the material that we shared? So substrate utilization rate, okay, it depends on the, it's proportional to the concentration of biomass, right? So yeah, dx by, no, it's changes substrate utilization rate, ds by dt, but it's proportional to x, right? And we can put a proportionality constant which is mu, right? So this is a specific you know, like substrate utilization rate, but here instead of mu we are going to use q. So q is the maximum specific rate of substrate utilization. So what I am saying here, maybe I clean the board and start writing from scratch, I think that would be better.
Can we directly replace mu by j?
No, we cannot directly replace, so we have to do some concept, because
Parameter switch.
yeah, so one is current, one is COD, right? So we cannot directly switch. So RSU equal to so basically ds by dt, okay. I can put either minus here or minus here, okay, it doesn't matter, it's decreasing over time, which is proportional to the, so proportional to the concentration of biomass, right? Concentration of biomass. But now what I am saying, so mu, so typically what we write, typically we write minus RSU equal to mu x, right? But mu x, but here we are saying mu is for like regular heterotrophic microbe, okay, but for those electroactive microbe we are going to use a term called q, okay. So just you can put mu, but they decided, okay, you know what, there's a different types of microbe, so we use a different term q, okay. And so now we are saying that x, this substrate utilization rate going to depend on, okay, so for activated sludge process we considered X, right? But here we are saying this is gonna be XA, active biomass. Okay, so it's going to depend on active biomass. So it is almost the same thing what we did for activated sludge process, but just different, you know, like I would say different symbol that we are using. So XA, active biomass, and Q is substrate utilization rate, right? So now we know from Monod equation Q, Monod equation we know mu equal to mu max S Ks plus S, right? So here it's gonna be Q max S Ks plus S, right? Just the only thing I'm replacing mu with Q. So now what I can write, Q max XA S Ks plus S. Can we write this? Make sense? So exactly Monod equation, just I replaced mu with Q. Okay? And then I put it there. So now you see, and instead of X, I put just XA, active biomass. Okay? I could put X, honestly speaking, but you know, this is the one that model who developed the model, he put X, A. So just you know, to respect him, I am also putting XA. Other than that, it's nothing else. So it is the same thing that what we did. So now, so you can see we have almost a similar thing here. Okay, so this came from the Monod equation and substrate utilization rate. Okay, so now let's see next step. So now we are saying that XA, active biomass concentration for a biofilm, okay, can be calculated from EAB concentration in biofilm, which is, so now we are saying that okay, this active biomass XA, but we can actually estimate that from concentration of EAB biomass, which is XF, okay, XF and biofilm thickness. So if you multiply by the concentration of electroactive bacteria, okay, SVSS, by the thickness of biofilm, because it's a biofilm system, it's not a suspended growth process, right? So that's why we want to multiply the concentration by the thickness of the biofilm. So what we are saying, XA, I can replace that with XF and LF, which is thickness of biofilm, and this is concentration of EAB biomass. Okay, make sense? So now what I can do, I can replace that part with XF and LF. So I did that here, XF, LF. Make sense? We are good? Okay. So now what we are saying, now substrate, if when substrate is rate limiting, then current density will follow Monod pattern. So what we are saying here, this is a special system. Instead of growth, okay, substrate concentration, we can have actually, we can replace that with current density, with substrate utilization rate. So what about in that case, what about the substrate utilization rate or substrate flux, okay, it's gonna be actually current density in the system. So now so substrate utilization rate, this term RS, I'm gonna replace that with JS. So kind of, you know, now we are saying it's a flux of electron donor. Okay, so now RSU term I'm gonna replace with J sub for substrate. So substrate flux within a, you know, like for certain area. So in the biofilm, okay, so this is for biofilm. So substrate flux within the biofilm gonna be same as the substrate utilization rate. Okay, so J sub gonna be this. Okay, now we are saying that, okay, you know what, like substrate flux, okay, gonna be equivalent to current density. But one thing is, so current is Coulomb, right? Coulomb per second. If you say ampere, so it's Coulomb per second. So it's electron transfer rate. But our substrate in biological process, it's COD, right? So one thing is COD and one thing is current. So that means I cannot just directly consider, okay, this is my current, right? I have to introduce some term that can allow me to convert COD to current. And how I can do that? I can actually introduce another term. You can see here 0.14 Fe, right? So now let me clean the board. This is a key part here. Okay, now what I am saying that I can convert that. So that was COD flux, right? That is COD flux, but I want that to convert it to current. So how I can convert that into current? So I can introduce a term 0.14 Fe naught, okay, and then Q max XF LF S Ks plus S. So why 0.14 Fe? Okay, so 0.14 Fe, it came from two things. So when microbes, okay, so Fe, you remember that, you know, when we did half reaction including cell, we had what? Fe and Fs, right? So Fe plus Fs equal to 1, right? That's what we used. So a portion going to be utilized for cell synthesis, a portion going to be utilized for going to go to the donor, right? But here my product is current. So a portion of electron going to go for cell synthesis and a portion of electron going to go for current generation in the process. So we are introducing a term, okay, it's not going to be 100%, a fraction of electron or COD going to be my current, okay. So and it could be that Fe naught could be 0.9, that Fe naught could be 0.8, depending on, you know, like how much is going for current generation, okay. But why 0.14? That 0.14 is the conversion of COD to ampere, okay, and you can see here I put it there. So 1 mole of electron per 8 gram of COD. So COD, 8 gram of COD is equivalent to 1 mole electron. How? Do you know?
This one
Yeah, 1 mole electron.
from half cell reaction.
So from half reaction. So for example, oxygen reduction to water, right?
Yes.
How many proton I should put here? 2. And how many electron?
2 by 2, I guess, because when you balance oxygen, there H2O you have to multiply by 1 by 2. Multiply by 2.
2, right?
Then it should be 4.
It should be 4, okay.
And that one also, proton also 4.
Proton 4, okay, now it's balanced, right? So now oxygen, it's how many gram of COD? Hmm? 32, right? So 32 gram of COD. So 32 gram of COD is equivalent to 4 mole of electron. Can I write this?
Yes.
So now 1 mole of electron,
8.
8. So 1 mole electron means 8 gram of COD, right? So that's exactly what I wrote. 1 mole electron, 8 gram of COD. So now per mole electron, what is the charge? It comes from Faraday's constant, right? So Faraday's constant is saying like 1 mole of electron gonna give us 96,500 Coulomb, right? It's a value for F. So now what is ampere? Ampere is Coulomb per second, right? So they I can, in one day, I have how many second? I have 86,400 second, right? So now what I am getting, 0.14 coulomb per second. So coulomb per second is ampere, so I can actually replace coulomb per second with A. So 0.14 ampere is gonna be equal to 1 gram COD per day. So that's why I put 1.14 here. Okay. So now we are good to go. We converted everything. Our COD has been converted to current. Okay. So now that equation can be directly used. So what if we put kinetic parameter here like Qmax, XF, and biofilm thickness, if we put substrate concentration, if we put Ks, what we are going to get? It's M per meter square. Okay. But previously in this equation, it was substrate flux. It was more COD. You see here, gram COD per meter square per day. But here, it's ampere per meter square, right? So we already converted from current to, sorry, COD to current. Okay.
Current density.
Current density, yes. So now, what would be the value for Fe? How I can get that?
1 minus Fs.
1 minus Fs, but how you are going to measure Fs? So Fs sometimes it is difficult to measure. Okay. So what we do, we have a term called, so electron donor is going for end product. Okay, and another portion is going for cell, right? So here my end product is current. Okay. So if I know the COD removal efficiency in my system, how many gram of COD removed, I can convert that into coulomb, right? I already, we know how to convert COD to coulomb, but now I'm going to have some experimental data where I'm going to have current. I can also, current means it's ampere, right? Ampere is coulomb per second. So if I know the current, I can also convert that current to coulomb, right? So I have some, how many coulomb I should get from my COD removal and how much coulomb actually I'm getting experimentally. From this, I can calculate something called coulombic efficiency. So coulombic efficiency is the ratio of total coulomb actually transferred to the anode from the substrate to maximum possible coulomb if all substrate removal, actually all substrate converted to current. Okay. So Q coulomb and that is coming from current, and this Q substrate is basically how much COD removed in the process. Okay. So typically this is going to be less than 100%, right? Because anaerobic microorganisms or any kind of like aerobic process, you are going to have more sludge production, right? So only small portion, like 60%.
It's not like efficiency, it's more like yield, right?
It's more like you can say yield of current.
Yes.
Yeah, it's more like yield of current.
Because it would be efficiency, then we have.
But yield, I don't wanna use the term yield because sometimes yield is used for like how much biomass produced, right? So yield is how much biomass produced per gram of COD removed, right? So we don't use the term yield. We use so if you have, let's say, coulombic efficiency is 90%, my Fe, this one gonna be 0.9 and this is gonna be 0.1, because I cannot it's not very easy to measure, right? If my coulombic efficiency is 80%, I'm gonna consider my Fe naught is 0.8. If it's 70%, I'm gonna put 0.7. Sometimes coulombic efficiency can be much less than, let's say you can see 50%, but we expect that, okay, anaerobic microbes, okay, it should not go, your cell synthesis should not be that high. So that, what are the other electrons seeing then? So sometimes what happen, some non-EAB, some microbes, some other microbes, they can actually take some of the electron if you have a mixed culture biofilm, okay. So that could happen, but anyway, that's CE calculation or coulombic efficiency calculation can allow us to estimate Fe naught. Sometimes, but do you think your coulombic efficiency can be more than 100%?
No.
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 Actually, sometimes you might see it's more than 100%.
But But
Okay.
It will defy that equation.
Yeah. So actually, even in one of my experiment, okay, that was done in back in 2012, okay, we found that actually continuously, like our Coulombic efficiency is higher than 100%. Then we went back to the literature and we found that, okay, what happened? Those microbes, you remember phosphorus accumulating bacteria?
Yes.
In anaerobic condition, they take VFA and store them as biopolymer. Those microbes can also do that. So when you enrich, you actually run the system with very high acetate, okay, concentration, and sometimes they actually store the acetate, okay, as some intracellular biopolymer, okay. And what happened later on, they start oxidizing those biopolymer and transfer electron. So that's why, yes, you see, like, your substrate is providing some electron donor, but you are getting actually more current than you should get. And that additional current might come from actually those oxidation of biopolymer. And actually this is actually an confocal image of we could see like some biopolymer accumulated within the biofilm. Okay.
So did someone explore this storing of electrons inside the
There are few paper we reported, but that was not our like primary focus. My PhD research was more focusing on kinetics, so I did not further investigated this. We knew that, okay, that thing could happen. We reported that, but we did not dig much. Okay. But yes, you might see, so if you see sometimes your Coulombic, if you're obviously, if you kind of in future, if you plan to work on this area and if you see Coulombic efficiency higher than 100%, I think that could be one thing could happen. Okay. Not necessarily it's something wrong that you did. So let's go back to our topic. So now we have this equation. Okay. So now if substrate is not rate limiting, so substrate is not rate limiting means your substrate concentration is very high. Okay, it's much higher than your Ks value. What is Ks? Ks is when actually growth is, or here it's current, right? It's Jmax, because we are not using mu. So your Ks gonna be Jmax divide by 2, right? At concentration where Jmax divide by 2. So if you are running your system at very high substrate concentration, then actually your Ks very higher than substrate concentration higher than Ks, then actually that part we can consider, okay, Ks is kind of very negligible, okay, compared to value for S. So that part I can consider. This is gonna be, so if S, Ks plus S, if I consider this is kind of quite negligible and this is quite big, this is gonna be 1, right? And at that time we can get Jmax, maximum current. So maximum current means Jmax equal to 0.14 Fe naught Qmax XF LF, because that term gonna be 1. So now I can actually put it back here for Qmax. Okay. So sorry, Jmax. So you can see this part we can actually replace with Jmax, right? So what I get, J equal to Jmax, S divide by Ks divide by Ks plus S. So which is almost same as your Monod equation, right? So if your system only the substrate is rate limiting, okay, and if you run your system at different substrate concentration, okay, your current gonna follow this pattern. Actually this graph is from one of my experiment that I did. Okay.
How did you do simulation here?
Oh, then we actually feed the model and see whether it can actually follow the mono. So those are my dots are my experimental data. Yeah. Yeah, and yellow is simulation, and you can see it's kind of following. Yeah, yeah. But later on, researcher actually extended this model. They try to add more component, because this is Monod is more microbial metabolism. But in here we also have a lot of electrochemical component, right? So then this model was further extended, combining some researcher combined that with Nernst equation, okay, for like electrochemistry. So that was actually combined. Sometimes they call them it's Nernst-Monod equation, okay. Then also some researcher actually combined that with Ohm's law, okay. So Nernst-Monod Ohm equation, okay. Even some part of my PhD thesis I kind of introduced Ohm's law, and I was measuring biofilm conductivity and see if we can actually feed that model as well, okay. But in most cases, okay, this part, microbial metabolism or intracellular kinetics, is the rate limiting. So other part, even if you add, okay, it doesn't matter, okay. So Monod equation in most cases can like I would say represent your system, okay. And we are going to actually, I have an example on this model, okay. So we are going to learn how to estimate Coulombic efficiency. We are going to learn how we can estimate current density using this equation, okay. But before that I have 2 or 3 more slides, I think. So current status of microbial electrochemical technology, as I mentioned, it's still in lab scale, but some product like biosensors have been actually commercialized, okay. Another product has been commercialized in Europe. So there is something called constructed wetland, okay. So they try to combine microbial electrochemistry with constructed wetland, and they did some actually demo, I think in some country in Europe, okay, couple of years ago. And but still, if you are thinking about waste or wastewater treatment, it's kind of still like we need to do a lot of work to scale up the process. And another thing, we always say, okay, that process can help us to recover energy as electricity, okay. Still current density maximum that we get from 10 to 25 amps per meter square, which is still not practically feasible. And this 10 to 25 amps per meter square or current density we can get with acetate, right, from your fundamental study. But if you use real domestic wastewater, it's still less than 5 amps per meter square, okay. And another challenge is how to scale up the process, because when you have, as I was mentioning, you have large reactor, means you have more ohmic losses, right. So that could be a big challenge here. So some researcher, they propose that, okay, instead of making one big system, why not we make like multiple small system, okay, and kind of add them in series or or parallel connection, or that might be a solution, okay. Another like if you look into this equation, if you have more active biomass or more EAB, okay, we can actually increase J or current density. So we are thinking, okay, what if instead of one electrode we put multiple electrode, but both it's still actually facing a lot of challenges. For example, even during my PhD I did a study with 4 electrode, and what I found, actually 4 electrode you don't linearly increase the performance, and 4 electrode they have different microbial community, different kinetic feature, okay. So it's kind of like quite challenging to achieve, like so putting 4 electrode not gonna give you 4 times performance. So we still have to do a lot of things in terms of design and in terms of fundamental as well, okay. So for example, like we have to better learn how that EET thing works, okay. Still we need to know about microbial competition, okay, syntrophic interaction, because if you want to use complex wastewater, then syntrophic interaction between EAB and non-EAB or fermentative bacteria are going to be very critical. So now the question is how we come up with a balanced biofilm, like combining all those different types of microbes, right? How to actually establish this kind of biofilm. And rule of biofilm thickness. Now we don't know, okay, how I can control the biofilm thickness. What is my optimum biofilm thickness, right? So this thing actually can have a lot of impact in your process. And substrate and pH gradient as well, okay. So there, this is actually those two component, they are kind of intertwined: thickness, substrate, pH. So we have to do a lot of work, okay, and that's what we have been doing, okay. I would say 15 or 20 years ago, when you know, like people's first test, not I think 20 or 25 years ago, when actually people started working on this, it was very hot topic. Everyone jumped, okay. They wanted to do something with this, but then later on, you know, when they kind of found, okay, there are a lot of bottlenecks, okay. Now community is getting smaller and smaller, okay. In Canada, I think only me and I think my another colleague, just two groups we are working on this right now, okay. But it used to be very large group actually, research community. So, so yes, there are a lot of, you know, you can see, you can have lot of different application. It's a very promising and emerging, but at the same time, okay, it comes with lot of challenges, and we have to overcome that if we want to actually push it to the market. So before I finish, I have two example, okay, calculation, because I love calculation, okay, in my class. So let's see how we can calculate Coulombic efficiency, and we are gonna, the kinetic equation that we developed, we are gonna learn how to apply that kinetic equation to estimate current density from a system, okay. So the first example, a lab scale MFC 28 ml is operated under fed batch mode 35 hours with acetic acid 1 gram per liter. Based on the following information, calculate Coulombic efficiencies, okay. Current density is 0.2 milliamp per centimeter square, anode surface area 7.1 centimeter square, acetate is completely utilized by EAB. So to estimate Coulombic efficiency, what I need? I need, okay, how much Coulomb I got from substrate, right, or electron donor, and how much Coulomb I am getting from as electricity, right. So the ratio of both can actually give me like Coulombic efficiency. So now, so Coulomb, Q Coulomb, which is basically coming from current density, and Q substrate is basically coming from your acetic acid. So now Q Coulomb, so current density is 0.2 milliamp per centimeter square. So now ampere, so Coulomb is basically ampere is Coulomb per second, right, Coulomb per second. So I have to convert that current into Coulomb. So how I can do that? So I have milliamp, 0.2 milliamp per centimeter square. So what I am going to do, I am going to convert that into amp. So I can divide that 0.2 by 1000 milliamp, and it's going to be amp. And I have the, so this is current density, right. So I have to multiply by the anode surface area, which is 7.1 centimeter square. So I multiply by the centimeter square, 7.1 centimeter square. So I get rid of centimeter square and centimeter square here, right. So I only have milliamp. Now I operated the system for 35 hours, okay, 35 hours, but current is Coulomb per second, right. So I have to convert that hour to second. So 3600 second equal to 1 hour, right. So now what I am getting, 178.92 Coulomb. I don't need, because I am getting rid of it, right. So what I am you got it? Yeah, I don't need to convert this, because I have centimeter square, and centimeter square I can just, you know, cross out. So now this is actually coming from current density. So how much Coulomb is coming from the substrate? So we have 1 gram per liter of acetate, and that is completely utilized, right. And we have 28 ml the volume, right. So volume multiplied by concentration is, I can get mass of COD, right. But now this is 1 gram per liter of acetate. So I have to convert that concentration to what? COD. You remember in second day 2 we learned how to actually estimate COD equivalent for some compound? And what was your first practice problem? Did you have a chance to have a look? So first practice problem was estimate COD equivalent for acetate, right? So what was the COD equivalent for acetate? 1.07 gram of COD per gram acetic acid or acetate. If you go back to the day 2 lecture note and if you check your practice problem, it's there. We already did that. So COD equivalent 1 gram of acetate gonna give you 1.07 gram of COD. So that's why now I put 1.07 gram of COD and I have the volume of the reactor. So concentration multiplied by volume, so I can get the mass of my COD, right? So 0.028 liter, and now COD need to be converted to what? Coulomb. And we know that 8 gram COD, 1 mole electron is 8 gram COD, right? So now what I do, I convert the COD to mole of electron. So 1 mole of electron per 8 gram of COD. And now I know the charge of electron. So 1 mole of electron from Faraday's constant, it's 96500 coulomb per second, right? So sorry, per mole of electron. So now I am getting, this is the amount of coulomb I should get, okay, if I completely recover all the or completely utilized all the COD for current generation, right? So this is what I should theoretically get, but I am getting practically 178, right? So my Coulombic efficiency is 178.92 divided by that theoretical coulomb 361.39. So basically 50%. So that means 50% of the COD, okay, went for something else, cell synthesis, maybe some it utilized by other non-EAB microbes, okay, and only 50% we recovered as current in the system, okay. So that's kind of also allow us to estimate what is Fe naught, right? So the second problem, and that's the last slide for me. So calculate the maximum theoretical current density for a MAC fed with sufficient acetic acid. Again, acetic acid means 1.07 gram COD per gram of acetate, and Coulombic efficiency is 80%. So my Fe naught is 0.8, right? So in this equation my Fe naught is 0.8. And other kinetic parameter, I have Qmax 540 milligram acetate per gram VSS per hour. I have XF, which is 2.8 10 to the power 5 gram VSS per meter cube. LF, which is biofilm thickness, right? So I have value for Qmax, I have value for XF, I have value for LF, right? So first thing we have to do, you can see here Qmax, this is given as acetate, but I need to convert that into COD, right? So what I am going to do, 540, I am going to first multiply by 1.07 and convert that into gram per gram VSS, okay, because I think other thing are provided in gram, right? So it's better to actually convert that into gram. So 540 milligram acetate per gram hour, I am getting 0.58 gram COD per gram VSS per hour. Okay. So now, so this is my equation, okay. Substrate is not rate limiting. So they are fed with sufficient acetic acid. So that means I am considering Jmax, right? So my substrate is not rate limiting anymore. So now 0.14, Fe naught is 0.8, right? Because Coulombic efficiency is 80%. So this is going to be 0.8. Qmax we already converted. XF is given 2.8 into 10 to the power 5 gram VSS per meter cube. LF I already have 5 micrometer. So 0.14 multiplied by 0.8, I have Qmax, I have value for XF, the biofilm thickness, I have to convert that into meter. It is provided in micrometer. So that's why I divided by 10 to the power 6, and now you need current. So that means it's gonna be per second, right? So sorry, it was in hours. So I can actually convert hour to day, right? So I can. So you have 2.18 amp per meter square. This is the current that you can get from your system. So that means if we know the kinetic parameter, if we know the Coulombic efficiency, we can estimate what is the current. Okay. So that's kind of a simple approach to model this kind of system. Okay. Any other question? Very good. There is some unit issue.
You can recheck.
Okay, I can check later. Yeah.
In that hour day, because it should be opposite. Because Qmax we have per hour. So basically, you are trying to replace hour, cancel out hour somehow.
Oh, actually, why I put that? Because 0.14A is basically gram COD per day. That's why a hour was converted to day.
Okay, so here the unit is 0.1.
Yeah, the unit I did not put. Yeah, yeah. Yeah, so basically, 0.14A, when we put that, this is for 1 gram COD per day, right? So that's why I converted hour to day.
This model is good, sir, but has so many limitations.
Yeah.
And has it been validated for any available data?
Actually, yes.
Put
It
into practice.
you can. So I can tell you the graph that I put here. Actually, this is my experiment from my own experiment. Okay. So yeah. So that means you can say model actually works.
That is well and good, sir, but we have kept so many limitations here.
Yes. Yeah. So it's a biological system. It's a very complex system, right? So.
With the Electron results, this cannot be implemented in practice.
So what kind of limitation you think that we need to overcome?
So for example, Ks. S is far more than Ks. That is one limitation.
So how it can be a limitation? You can provide substrate more than
That
Ks.
is only if J is equal to J max S D by J, it follows one out kinetics. So like that, so many other thickness of film, thickness of film is a variable in fact. That depends upon normal.
But you are actually using thickness in your model.
That is also a variable.
Yeah, that is also. So if you change your LF, obviously your number gonna change, right?
So like that, some hypothetical, reasonably acceptable assumptions are there. My idea is, if this model is holding good, it has to validate with the experimental results. As
It already has been validated with experimental result. What I am saying, this is my experimental result. You can see I feed that model there.
That is okay, sir. My plan, my idea is, in practical situations, will that, has it been implemented?
So that's what I was telling in my very last slide. Okay,
That is not a limitation, that is a condition in which it applies.
That's what when
so if you see practical, if you say
it's an ideal condition where all the conditions are defined.
so if you say practical application, practical is more like scale up issue. It's not about like model. It has nothing to do with model.
So for practical application, he already mentioned about biosensors. So it's
And-
already, and he also mentioned about a plant in Europe where he can also do the wastewater treatment, actually in sync with the wetland, right?
Yeah, and
So
one
those are
thing
the
is
practical-
like you can go with instead of, so the major challenge is when you develop or fabricate big system, you have more energy loss, right? So now one thing could be you have multiple unit, but obviously multiple unit gonna cost more. So typically one big system costs less, right? Multiple small things actually going to cost you more. Now we don't know whether it's feasible or not. Another thing could be like we put more electrode, but we know that actually that doesn't work. It has been actually proved in even in bench scale it doesn't work. So how you expect that it's going to actually work in full scale, right? So it's not about a model problem. Actually monode model has been applied. So why I introduced that in the class, I was telling you that actually like this kind of kinetics, if you learn for one system, you can actually apply for other system as well. Let's say not necessarily, you know, like what topic we covered in this course, okay? Your research topic is something different, but you can take this fundamental learning and you can apply it for something else. And as you can see, like, you know, this is an emerging topic, but we can still use that monode equation and apply that to estimate current density, which is our actually the interest. But when we used monode equation to develop some design equation for activated sludge process, what we did, we try to predict effluent concentration. We try to predict our biomass concentration, right? So yes, model always has some limitation. You can extend, and that's what actually researchers are doing. And as I mentioned, some researchers actually extended this model to Nernst monode equation. Some people actually extended Nernst monode Ohm equation. Okay, so there could be a lot of extension, but what we found, so if only one term can actually fit your experimental data, that means those other component or other extension may not be that critical, so they are not rate limiting. This is the one is actually rate limiting. Okay.
This is the basic of all this.
Yeah, so this is basic of all, and this is actually the beauty of monode equation. It kind of like works.
For other model developments and applications.
Yeah,
Reference.
Huh?
Based on this information, we can develop some other
Yeah,
models.
yeah, obviously, yeah, there is always room for, you know, like you can extend the model if needed. There are a lot of things you can do, yes. Okay, so I'll stop here and thank you so much. And this is where I'm kind of finishing right now. And I think we already have another speaker here for today. I'm just going to get my, yeah. Okay, just give me a second. Let me clean the board.